So I'll get started because I usually do this in like an hour and I only have 30 minutes. So I'll skip the intro. I'll go straight to the real deal. And I really hope that the title of my talk, which is a bit cryptic, was enough to get you all here today. But if you want to know about me or whatever, just go to my website. Everything's there. So, skipping the intro, I'm not going to start this talk with anything too hard, with no programming. I'm going to start with a philosophical question. So there's this concept of Laplace's demon, which was coined by this guy, the French guy, Pierre-Simon de Laplace. And this concept relates to him thinking that the universe could be fully deterministic, which is a bit depressing because that means we have no free will. That means you can get a state of the whole universe and calculate both the future and the past. And this was a dream of many logicians through many, many years. This was, for example, the dream of Leibniz. So Leibniz, he used to say that if controversies were to arise, there would be no more need for disputation between two philosophers than between two calculators. He said that it would suffice for them to take their pencils in their hands and sit down at the abacus and say to each other, calculemus. So what he wanted to do was basically solve all disputations with calculus, which would be great, right? I mean, the universe would be much easier. And then quantum physics came along. Didn't work. So these two guys, Alan Turing and Alonzo Church, they created these systems for basically computing things, for encoding things as symbols and being able to get to results. So Turing was the guy that was responsible for Turing machines, which gave birth to, the very foundations of object-oriented programming. And Alonzo Church was the guy that did Lambda Calculus, which is what is behind functional programming. Now you're probably asking yourselves, why this is useful? Truth is, I don't know. Stack Overflow does. And if you search on Stack Overflow for whether it's useful or helpful to know Lambda Calculus, you see this answer. It says that if you want to program in any functional programming language, it's essential. Just to zoom in a bit, if you want to program in any functional programming language, essential. Get it? Cool, so let's get to Lambda Calculus. So in Lambda Calculus, everything is an expression, which means that everything evaluates to a value. So you can just get things down to a single value at the end. That's how you do Lambda Calculus. You get a bunch of symbols, you put them in, you evaluate, you get a result. So everything in Lambda Calculus comes from this token, an expression. And you can also have these other tokens, and you can see there that the definitions are recursive, which means you can have expressions inside these tokens. You have identifiers, which are just variables. You have an abstraction, which are just function definitions. You have function applications, and you have grouping. So I use this just to disambiguate things. Now, this is a lambda people lambda. And right there, you can see that's a meta variable, which is just an argument. And then there's the body of the function. Now, this is simple, right? Lambda calculus is just like this. So when you do this, when you write a arg, you're just applying arg to a, just a function call. And if you do that, that's the identity function, just get back arg. Simple, right? Easy. Now, the thing is, functions can only take a single argument. That's why I said it's easy, as you see. But lambdas can return other lambdas, so you can have this here. So you have a function which takes A, and then returns a function which takes B and returns B. This is also known as currying, for those familiar with Haskell. Great programming language, highly recommend. And this is what it would look like in JavaScript. So just to give you a more practical example, this is an add function that's curried. So it takes A, returns a function which takes B, which means it's really composable, because you can just create a function called add2, and you have 2 already inside it, kind of like in a state in a way. And then you can just do add2, and then you have to pass 2 all over again. So lambda calculus is just another way of representing computation. And it is string complete, which means we can replace any programming language with lambda calculus, including JavaScript. So I'm not the first one to do this. So Tom Stewart has done this in his brilliant talk called Programming with Nothing. He's done it with Ruby though. And I want to take this one step further. Want to run JavaScript, sometimes it doesn't really need to be run. Then I want to run JavaScript with some birds. And then I want to run JavaScript and the birds. And then I'll hopefully apologize and it'll be fine. So yeah, it's time. So I'll now just do live coding for probably the rest of this. And I'll start with replacing some booleans. This is a bit weird. Should be fine to write code like this. So yeah, so let's just open Vim. And yeah, let's start replacing some stuff. So yeah, so what I'm going to do here is, so right here you see that every time I save my file, you see some results. And there is where I write all the code. I hope the font size is fine. Is the font size fine? Yes? Okay. Cool. So let's replace some booleans. Let's replace true. So first I'll just write, true. And this scenario is going to select between yes and no. So pretty straightforward. We can just console log true. And well, we'll get yes. So here what we're doing is we're just selecting the first value, right? So we're giving it yes or no. We're selecting the first one. And if you get false, yep, I can increase the size. Yeah. This good? Okay, cool. And if we have false, so we'll have no. So you can copy this. Okay. Now the thing is, I don't like booleans. Just don't. So you can just replace this with a function which takes two things. So you can take yes and no, or whatever you want. Am I on caps lock? So I can just have a function which takes A, which takes B. And then it can return A, which is the first thing I've given it. It can take A, it can take B for false, and it can return the second thing. So now if I pass the same strings there, yes and no, so you can just do this, and we can replace this for false, we still get the same thing. Now we don't need booleans, right? That part of the syntax is over. We can even have not. So if you want to replace not, so not just inverts things. So here, you're going to get a boolean, which I'm going to call f. And then what you're going to do is you're going to apply those in reverse order. And now you can just invert these. You can just do this. And yeah, you get the inverse. So, oh, malformed error. Yeah, I forgot an equal sign. So there we go. And now you get no and yes. Done. But that's easy. And it's going to get more fun. Now we can also replace numbers. And numbers, they're a weird thing. First, to replace numbers, we need to ask what a number really is. Have you ever asked yourself, before sleep, what a number is? What is this? This is just a symbol which represents something. So numbers are just an abstraction, right? They just abstract away relevant details. Like these two oranges, they're not the same. But two just represents the concept of having two oranges. You just abstract away all the detail. So when you see those two glasses, that is just a symbol to represent something. The very concept of chi, it is a weird concept if you stop to think about it. So that there is just a representation. And when you have quantities, you have the actual meaning. So for you to replace number with functions, you can use function application. So here I have the 0, which just takes f, x, and just returns x, sorry. And then if you want to increase that and you want to get 1, you apply x to f once, and you just keep applying things to f. And you keep getting numbers. Now, I know this is weird. Like, I mean, how are these numbers? And how does this even make sense? So when you have numbers in your computer, those are just electric signals. Right? You're just abstracting away numbers to electric signals to a binary system, a binary representation, and then you're computing. So yeah, so we replaced some arithmetics because you know I don't like plus signs and stuff. So first thing I'm going to do is the sum function. So for you to sum something, right? When you sum two numbers, actually before that, let me get the numbers here. So let's write some numbers. So this is 0. And now, if you want to get other numbers like 1, and let's do this, and let's get also 2 and 3, and let's do this, and this, and this, and this, and this, and this. So first, to convert these to a representation we know, we can use a function which is just going to convert those to just decimals. So I'm going to call this to num. And this is not part of Lambda Calculus, okay? This is just so we can see results, so it's not too weird. You know, because everyone does this in their day job anyway. So yeah, so you're gonna have n, and I'm gonna do some mutation here. I'm gonna have I, and I'm gonna invoke n with a function which increments I. And then I'm gonna console log the value of I. So the way this works is, because we're just repeating f there multiple times, every time it gets repeated, it increments I, and then I log I. So now I can convert my numbers to things I can actually understand. 1 and 2 and 3. And if we save this, we get 1, 2, and 3. Okay, and now we can operate with these numbers, right? Like we can just do a sum. So we can have a sum, and we can have a and b. And we need to ask ourselves, in order to replace a sum, what a sum really is. So when you're summing 2 and 3, what you're actually doing is you're getting the successor of 3 twice. So you're getting 4, and then you're getting 5. So sum is nothing but repeating the successor function b times 4a. But we don't have the successor function, so we need to implement that. So first to get successor, before I get to sum, I'm gonna have to start with this, just the identity function, and I'm gonna just tunum 3 here, and I'm gonna tunum the successor of 3. There we go. So this is just gonna get back wherever we pass to it. We haven't defined 0, because I deleted all my numbers. Let's put them back there. There we go. So we have it back. And let me also remove this. So now we always get back 3 because we just have the identity function. And if we want to always get back 1, we can just replace this a with the definition of 1. So now we always get 1. Now, if you want to get a successor of a number, what you need to do is get basically another function application. So you can just, to get the same number, multiply f by a, and only then apply x. So I get 3 if I do this. And if I want the successor, I can just apply that to f once again, which then allows me to define 4 as the successor of 3. And then I can tunum 4. And now that I have sum, I can define 5 as the sum of 2 and 3. And I can also tunum that. Cool. So you don't need pluses and minuses anymore. And after that, we can also go ahead and try to replace subtraction. So subtraction is a bit weirder. Subtraction requires us to do a bit more work. So subtraction is the opposite of the sum. So I'm just going to paste sum here. But instead of getting the successor of a, I'm going to get the predecessor of a. Now, for me to get to predecessors, I need to explain what wrappers are, and I need to explain what pairs are. I need to explain how to increment pairs, and only then we'll get to the predecessor function. So the wrapper function, you might be familiar with this. This is just a functor. So we store something in it, we store a, then you pass it f, and we apply whatever is stored inside there to f. So let's do this. Let's have a wrapper here. So let's wrap a, let's take f, and then let's apply a to f. So I'm going to create what I'm going to call here a box. So these are just like weird names, and it's easier to understand. So if you have a box which wraps Brazil, you can pass console log to the box, and it logs Brazil. That's because we just replaced this f with console log, and we already had a there. So a was Brazil. So it evaluates to this, essentially. So now that we have a box, a pair, a functor, we can see what pairs are, because pairs are just like wrappers, but they take two values instead of one. And then you tell which value you want through f. So for you to tell which value you want, you can just use true and false, because if you look at this closely, you see that true just gives you the first thing it's passed, while false just takes the second thing. So if we go ahead and we increment a pair, so let's copy this. Let's get a pair, A and B, and now we can do this, and we can have a box which now has a pair. So I'm gonna just do this, and now we can get the things inside our box. So let's get the first and the second, and I'm going to console log that. So if we do this, we should get the right strings. First, not defined because of the string false. We need to copy it here and have it there. So we can just do this. First is true, while second is false. And we get the right strings. Okay, so now we have pairs. And after pairs, the next thing, so this is all to get to subtraction, okay? It's really easy and practical. So you need to increment pairs. So increment pairs consists of getting a pair, so two values, getting the one in the second position, copying to the first, and incrementing the second. So 0, 0 becomes 0 and 1, 1 and 2 becomes 2 and 3, 4 and 5, anyone? Anyone? 5 and 6, yeah. So now the interesting thing here is that if you repeat the increment pair operation over 0, 0 a bunch of times, like 5 times, you get 0 and 1, 1 and 2, 2 and 3, 3 and 4, 4 and 5. And then the first value there is the predecessor. So what you're actually doing here is you're storing the state of the previous computation. When you get successor, you're storing that in the first position of the pair, which is why you can get the predecessor. So let's write that. So let's write our increment pair here. So increment pair takes a pair P, gets the second value in P, puts it in another pair, and then in the second position, we get P second, and we get the successor of that. There we go. And now we can test this. We can write 0, 0, which is nothing but a pair with 0 and 0. So if we now do here result, so just first to see this, I'm going to start this in result, and I'm going to increment pair 0, 0, and we can do result first and result second, and we need to num this. So we get 0 and 1. If we repeat this twice, so twice increment pair, 1 and 2, 2 and 3, which means that finally predecessor is going to take a number n, and then it's going to repeat the increment pair operation n times for pair 0, 0, and get the first value. So now we can define, let's see what we can define. Let's try to define, I don't know. So we have 1, 2, and 3. Let's just get the predecessor of 4 and see if that works. So you get the predecessor of 4. And let's try to get the process of 3 and 3. And let's see if that works. Yeah, it does. Cool, now we can finally get subtraction. So do we have sub here? Oh yeah, sub is there. So it's easy. We can just, let's just do num subtraction 4 and 1, and that should give us 3. Okay, cool, it works. We don't need any more operators. You know, this is much more convenient. And also we can replace other things. We can replace multiplication. So when you're multiplying something, again, we have to ask ourselves, you know, what multiplication is, do the whole thing. So when you're multiplying something, when you're doing like 3 times 3, what you're doing is you're repeating the function, we repeat something, and you're repeating it for a particular value, and then you're repeating that again twice, and then you get 6. So here we're just gonna get a and b, and then we're gonna repeat f b times, and we're gonna repeat the result of that 8 times. So that allows us to now define 6 as mod of 2 and 3. And we can also define 5 as the predecessor of 6. And we can tunum those, 5 and 6. And 5 has already been declared. Oh yeah, I defined 5 up there. Cannot access 6 before it is defined. Oh, because I'm trying to get a predecessor of 6 here. There we go. And then f is not defined because I haven't taken it as an argument. Yeah, okay, the magic of live coding. So yeah, so we get 5 and 6. We get everything we need. We can also replace exponentiation. So this is going to be just like matplotlib. So when you're doing like 2 to the 3rd power, what you're doing is you're repeating a function which repeats something twice, 3 times. So just as if you're doing this, which means this is just this. Just repeating the function which repeats something b times, which now allows us to define 8 as 2 to the 3rd. We can also get 7 if we want, which is just the predecessor of 8. And let's see if that works. Predecessor of 8, because 8 was not defined. 3rd is not defined because this is 3. And yeah, 7 and 8. Okay, so there we go. We got exactly what we needed. We got all these operations. And yeah, here's what I've just told you. So I'm running a bit because, you know, I usually do this in an hour. There we go. We now get to replace Boolean operators. Say, you know, greater than, equals, whatever. It's just too much syntax. So we can go ahead and replace some of those. We can replace things like and. So and is going to take a and b, so 2 booleans. And if a is true, we can return b. So that if b is true, well, that's going to be true. Otherwise, if it's false, we return a because it's false anyway. And we can have or, which takes a and b. And then if a is true, it needs to return a because we want true straight away. Otherwise, we try to return b. So now, if we go ahead and we test this, let's console log some values here. So let's try and true and true. And let's try this with yes and no. And let's copy that a few times. So now we are going to do all the possible combinations of this. So true and false, false and true, and false and false. And there we get yes, no, and no, because this is an and only the first one has 2 truths. And if we replace now ands with ors, so we should get yes on the first 3 ones. And we do. So if you want to have an if, by the way, that's really easy because we already select things with Boolean. So an if just gets a Boolean and returns itself. You know, it's just syntax sugar, as all of this really is. And going ahead of those, we can also do definitions of like less or equals. So for you to know if something is less or equal than another number, you're going to take a and b. And because here, if we subtract 2 numbers, we can only get to the floor of 0, because these here we only represent positive numbers. There's ways to represent negative numbers, but I'm just representing positive ones now. You can simply subtract b from a, and if that is 0, you're going to have a number that is less or equal to b. Because, well, if b is greater than a anyway, you are going to get 0. So let's do this. So let's define a 0. And let's try to think about how do we detect whether a number is 0. So if you look closely at 0 and false there, you see they're the same thing. Right? They just take two things and they return the second one. Which means that if you want to check if something is 0, you can take n. And if n is 0, it's going to return the second thing, which means it returns true. Otherwise, it returns always false. But we cannot do this because we keep applying things to f, which means that we have to do this. So we have a function which always returns false, no matter how many times it's called. So we can test this with is 0. So let's do is 0 for a bunch of numbers. I'm going to do this, and let's try 1. This, actually, I only need this, and let's do it for, I don't know, 0, 1, 2, and 3. And if we do this, so only the first one is yes, because only the first one is 0. Now for less or equals, we can go ahead and replace this, and let's test whether it works. So here 2 needs to be less or equal to 2. Then we can also have 3 and 1. That should be true as well. And now here let's try 3 and 1. So now this should be true. This should be true. This should be false. Yes, it is. Okay. So let's go ahead. Let's replace other things. Let's replace greater than. So greater than is just the opposite of less or equal. Right? If a number is not less or equal to another number, it's greater than number, which means you can just do not less or equal a and b. And if we do this, start to do gt, not g and t, gt. You get 1 and 3, 3 and 1, which means the only one that's going to be yes is the last one. And there we go. And we can also have equals. There you go. So for equals, we need to have a number that's less or equal to another number. And the opposite should also be true. So if we do this now, equals, yes, no, no. Okay, we've replaced everything, I think. So now that means we can go ahead, we can replace an actual function. So before I bring JavaScript with the birds, I'm just going to paste the function here. I'm going to invoke it so I get to all of its branches. So let's do, I don't know, 2 and 3. To get to the second one, let's do 4 and 3. And here, let's do 3 and 4. And let's console log this. There we go. And we get 9, 1, and 12. But this is too much syntax, right? It just looks ugly. So we can go ahead and replace this with functions that take a single argument and just return other functions. So what we're going to do here is we're going to go ahead and we're going to replace this first statement here. So if a equals b, we're going to get to do this, which is multiplying a by 2. And then we're going to sum b to that. And we go ahead, we get to the other branch. So if a is greater than b, we now get to this branch, which does, let's remove this, which does a minus b. And otherwise, we multiply a and b. So is that the same thing? Yeah, that's the same thing. Let's check the parentheses, see if this Lisp code is right. Yes, it does look like it is. So if we now get to num, and we do this, and we replace this, what numbers did I have? Let's replace these first. And now let's do this and this. I'm gonna eat up your questions time, I'm sorry. And let's see what we get. So if I save this, I get the same. Running time, 30 minutes. So yeah, I can replace everything here with just functions. And you can even go further than that. So I'm gonna end this quite quickly. So you can replace that with combinators, which are just birds, which are basically functions which only have bound variables, which are variables that don't come from the context. So this is a function which all variables are bound. This is not, because you have y there. And you can go ahead and basically, the reason I'm going to ruin this with birds is because of this book by Raymond Smullin, in which he asks you to prove the existence of birds just using logic. So he just gets birds and uses them to replace these functions here. So these combinators. So you have the bird, which replaces the if, the identity function, the Costa, which is just true, the kite, which is just false, and so on. Which means that, there's also Y Combinator, which is just a combinator to the recursion, which is why Y Combinator has the name it has, because it is a company that stars other companies. I've written a blog post about that in case you want to see it, but yeah, just to make it fun, that just means you can replace things with birds, and that means you can just go here, and you can copy this, and you can replace these functions with these definitions, because at the end of the day, they're nothing but the combinations we just seen, and you still get the same results. And it gets it even better, because you can replace more and more functions by just replacing things with more and more combinators. So things just get shorter and shorter, up to the point that you can also ring the birds, because you only need 2 of them. You only need S and K. Some people also call this SKI calculus, because it's more convenient to have I, because everything here is very convenient. But I can actually be derived with S and K. So the kite can be this, the bluebird can be this, the cardinal can be this. There's also J. I don't know if anyone wants to try guessing. No? Okay. So yeah, so all these are here. And that just means that if you can replace all code by functions, all functions by combinators, and all combinators by S and K, that means you can write all the code you've ever written only with S and K. Yeah, so everyone's gonna love you at your job. And yeah, I just wanted to actually apologize, because 1, I'm over time, and 2, I've probably ruined your life. I've made you question whether free will exists and stuff. But yeah, that's just the intro, because that's the very beginning of what functional programming really is, of computability theory, which is going to make you question your whole life. And yeah, of wanting to hang pictures of Ghetto in your room. So yeah, that's pretty much it. A bunch of refs here. These are going to be online. Do we have time for questions? Yes, we do. Cool, thank you.